Well, this is the third video on separation axioms. Here, basically, we prove four theorems. These theorems give a set of hypotheses under which normality of a space is assured. Okay. Well, at the end of this lecture, so one should be able to prove that compact and Hausdorff spaces are normal, and the second thing is matrix spaces are normal. That is all the topological spaces which are metrizable are normal spaces. Okay. Then the third result is regular second countable spaces, okay, are normal. And the last one, that is the fourth one, every well ordered set, okay, equipped with ordered topology is normal. Okay, so we have four theorem. So we prove here. So let us move to the theorem. The first one, the statement is every compact and Hausdorff space is normal. So recall that a topological space X is called compact if every open cover of X admits a finite subcover. Okay. So this is the general definition. Every open cover has a finite subcover. So then the space is called compact. And what is Hausdorff? Every two distinct points can be separated by open subsets. That is, for X not equal to Y in the space, topological space X, there are disjoint open neighborhoods containing the points X and Y. Okay. So here we prove that every compact and Hausdorff space is normal. So recall the definition of normality. So topological space X is called normal if for given every two disjoint closed subsets in the space X. So let us denote the closed subsets by A and B. Okay, so A and B are closed subsets of X, and A intersection with B equal to empty set, that is, they are disjoint. Then there are disjoint open neighborhoods of A and B, that is, there are open subsets U and V in the space X such that they are disjoint, that is, U intersection with V equal to empty set, and their neighborhoods of A and B, that is, A contained in U and B contained in V, that is, A is subset of U and B is subset of V. U intersection V equal to empty set, and U and V, they are open in X. Okay. So what to prove every compact Hausdorff space is normal. So well, here we use the fact below. So we in the proof we use the fact. So what is the fact? So if X is compact and Hausdorff, Okay, if X is compact and Hausdorff, and X is a point in the space X, and B is closed subset of X, such that X does not belong to B, then there are disjoint open sets U and V in X containing X and B. So here is the picture. B is closed subsets. B is closed subset in X, and X is a point in X, such that X is not in B, that is X is in the complement of B, so X belongs to X minus B. So here we have closed subset B, and here we have point X. Then there are open sets U and V, disjoint open sets U and V containing X and B. Okay, so if X is compact and Hausdorff, and X is a point in X, and B is closed subset in X, such that X is not in B, then we have disjoint open sets U and V containing X and B. Okay, so this is happen if X is compact and Hausdorff. Okay, so this result basically we have proved earlier. We use this result in the proof of theorem 1. Okay, so we have to prove that X is normal. So let us consider two arbitrary disjoint closed subsets A and B in X. So A comma B, they are closed subsets in X, and they are disjoint, A intersection B equal to empty. So what to prove? We have to prove that there are open sets U and V in X, such that U intersection with V equal to empty set, and A contained in U, B contained in V. Okay, well, so here the proof starts. For a point little a in the closed set A, we have UA and VA open subsets in X, such that A belongs to UA and B contained in VB, and their disjoint UA intersection with VA equal to empty set. Basically here what we are doing, we are using the fact stated here. Okay, so instead of, so here in the place of X we are considering the point A, and B is the set here. This is the set B. Okay, so if A is a point in A, and so consider the pair of point A and the closed subset of X B. So for such a pair, so you know A is not in B, because A intersection B is equal to empty set, and the point A, this is in the set A, so A does not belong to B. So that is a perfect pair to apply this fact. So the point A, little a, and closed subset B, for such a pair we have a disjoint pair of disjoint open sets. Here we have denoted by UA and VA corresponding to such a point A. So they are disjoint open subsets of A. So this is the condition, UA intersection with VA equal to empty. So that is UA is and VA, they are disjoint, and UA contains A and B subset of VA. Okay, So here we have applied the fact stated in the previous slide. Now consider such a collection for every A. Take UA. Okay. So this is a collection of open sets, and this is also a cover of A. So this is an open cover. So this is an open cover of A, and A is closed subset of X. So that is we have considered the first item, and what is our hypothesis? X is compact and Hausdorff. So A is closed subset of a compact topological space X. So A is also compact. So this is open cover of compact set A in the topological space X. So this open cover admits a finite subcover. So consider a finite subcover U sub AI I equal to 1 and so on to K. This is finite subset of this open cover, and this is also a cover of A. So this is finite subcover of A because A is compact, such a finite subcover exists. Okay. Now so corresponding to so UAI, we have VAI. So here is the construction. So for every UA, so for every UA also we have VA, and they are disjoint. So for every UAI we have VAI such that UAI intersection with VAI equal to empty set. Okay, so we define U equal to this finite union UAI. I runs from 1 to K. Okay, where this is a finite subcover of A. So we define U equal to union UAI I equal to 1 to K. So of course this is union of open sets UAI. So U is open, and V equal to intersection VAI I equal to 1 to K. So this is intersection VAI. So this is equal to B. So now it is easy to see that A is subset of U because this is open cover. This is open cover of A. That means A is subset of this union UAI I equal to 1 to K, and this is equal to U. Union is equal to U. So A is subset of U. Okay, so what we have, U is open subset of X, and A is a subset of U. And so here we define V equal to finite intersection of open sets VAI I equal to 1 to K, and each VAI contains the closed set B. Okay, so V contains B. So B is subset of V, and B is finite intersection of open sets. So B is also open. Okay, so thus we have a pair of open sets U and V containing closed sets A and B respectively. So what remains to prove? So we have to prove that they are disjoint. Okay, so here, so this is the point. A is subset of U and B is subset of V, that we have already explained. So now it remains to prove that they are disjoint. Okay, so if there is a point in the intersection U intersection V, suppose X belongs to U intersection B, then there exist so then there exists a point U intersection with V. So X is in V means X is in every VAI, okay, and there exists some J such that X belongs to UAJ, okay. So X belongs to UAJ and X belongs to every VAI. In particular, X belongs to UAJ, VAJ. So X belongs to UAJ intersection with VAJ. But that is a contradiction because UAJ intersection with VAJ equal to empty set. Okay, so therefore, what we have derived that is U intersection with V equal to empty set. Okay, this completes the proof. Okay, now we move to the second theorem. So this is the statement: every metric space X comma D is normal. So X is underlying set and is metric on the set X. So this is metric space. Okay, X comma D, that is metric space. So what we prove is X comma D, that is normal. So X. So consequence of this theorem is every metrizable topological space is normal. Okay. Okay, let us start the proof. So to prove X is normal, so consider a pair of closed subsets A comma B. So let A comma B closed subsets in the space X and their disjoint A intersection with B equal to empty set. Okay, so for A belongs to A, there exists some positive real number. We denote it by epsilon A greater than 0, such that the ball B with centered at A and radius epsilon A. This is open ball with centered at A and radius epsilon A. Okay, so this open ball intersection with B equal to empty set. So why this is happening? Because B is closed subset of X and A is in A means A belongs to complement of B. Okay, so A intersection with B equal to empty set and A belongs to A means A does not belong to B, so A is in B complement. Okay, so A belongs to B complement and B is closed, so B complement is open, and by definition of open set in a metric space, so what we have, there exists some open ball B A comma epsilon A that is contained in B complement. Therefore this open ball intersection with B, that is equal to empty set, and similarly for interchanging the role of A and B, what we have for every little b in the closed set B, there exists some positive real number denoted by epsilon B, such that the open ball with centered at B and radius epsilon B intersection with A equal to empty set. Now we consider so U equal to union of open balls with centered at little a and radius epsilon a over 2. So here so we have uh, reduced um, the radius by epsilon a over 2, okay, and union is over a belongs to, so here the union is over the index at a, okay. So U equal to union open balls with centered at a and radius epsilon a over 2, where a belongs to the closed set A. Now for every little a, so little a belongs to this open ball, which is the center of the ball, okay. So this closed set A is a subset of U, and U is open. So basically this is union of arbitrary union of open sets. So U is open neighborhood of A, and similarly V equal to union balls B with centered at B and epsilon B over epsilon B over 2 radius, okay, and B runs in the closed set B, okay. So B is open neighborhood of the closed set B. So what we have open sets U and B containing A and B respectively. So to show this is normal, so it is enough to, now it remains to show that U intersection with V equal to empty set, okay. So we have U comma V open in X, so this is union of open balls, so U is open and V is also union of open balls, so V is also open. So U and V, they are open in X, and A is subset of U and B is subset of V, okay. So it remains to prove that they are disjoint, that is U intersection with V equal to empty set, okay. So here is the proof. So the proof is by contradiction. Suppose there exists an element X in the intersection U intersection with V. So X is in U and X is in V. So X is in the intersection. So X is in U means there exists some A such that X belongs to B A comma epsilon A over 2. So if X belongs to U, then there exists some little a such that X belongs to B A comma epsilon A over 2. So then here is the statement: if X belongs to this intersection, then X belongs to B A comma epsilon A over 2, and similarly X belongs to B, the ball with center at B and radius epsilon B over 2 for some A and B in B. Okay, so now the distance between A and B. So here we have used triangle inequality with vertices of the triangle at A, B and X. Okay, so this is the point X. So distance between A and B, and this is less or equal to distance between A and X plus distance between X comma B, X and B. So this is the triangle inequality, and you know X is in this ball, so this quantity dA comma X, that is less or equal to epsilon A over 2, and this is less or equal to okay, so this is open ball, so this is strictly less than epsilon A over 2, and this is X dx comma B, that is strictly less than epsilon A B over 2. So these two, so sum of these two quantities, this is strictly less than epsilon A plus epsilon B over 2. Now we have two cases. So if epsilon A is less or equal to epsilon B, then we have A belongs to the ball with center at B and radius epsilon B. So here is the argument. Then so if epsilon A is less or equal to epsilon B, then what we have d A comma B, that is the distance between A comma B, is strictly, so this inequality we have from the last item. So and this implies d A comma B, that is strictly less than epsilon B. Okay, so epsilon A is dominated by epsilon B. Okay, so replace epsilon A by epsilon B, so we will get epsilon B on the right hand side. So distance between A and B, that is strictly less than epsilon B. That means A belongs to the open ball with center at B and radius epsilon B. Okay, but let us go back to the construction. So here we have constructed epsilon. The ball B with center at little b and radius epsilon B intersection with A equal to empty set. But here what we have, A belongs to the set A, and A also belongs to this ball. That contradict that this ball intersection with A is empty set. So this is a contradiction. And similarly, when epsilon B, so here we have considered so the case when epsilon A is less than or equal to epsilon B, and in the second case epsilon B is less or equal to epsilon A. So if epsilon B is less or equal to epsilon A, then similarly, so interchanging the role of A and B in the last item, so in this item, so we get B belongs to this ball, the ball with center at A and radius epsilon A. So this is again contradiction, because this ball intersection with B, the closed set B, this is empty set, but here we get B belongs to this, and B of course belongs to the closed set B. So this is again a contradiction. Therefore we conclude that U intersection with B equal to empty set. So this completes the proof of theorem 2. Okay, let me stop this video here, and in the next section so we will prove two more theorems. So that is regulars and second countable spaces are normal and well ordered sets we equate with order topology. So these are